divergence theorem. S is a piecewise, smooth, closed surface that encloses a solid W in space. S is oriented outwards. F is a vector field with continuous partial derivatives. Then the outward flux of F through the closed surface is the triple integral of the divergence of F over the solid that is enclosed by the surface. Just like we do with Stokes and Green, we're going to verify the divergence theorem. Region bounded. X squared plus y squared equals 4, z equals 0, and z equals 3. This is the surface. This corresponds up here to z equals 3. And this down here corresponds to z equals 0. For the flux. So we have to parameterize these circles. But we have three separate surfaces. We have this top bit, we have this bottom bit, and then we have the lateral part as well. And so we're going to define the flux through the top, through the bottom, and through that lateral portion. Well, that top surface isn't just a circle. What's the radius of the circle? 2. And it's on the plane z equals 3. Sorry. Should be R. R is going to go from 0 to 2, theta is going to go from 0 to 2 pi. Normal vector for the top would just be 0, 0, R. The bottom. Well, again, it's just a circle of radius 2, right? But now it's located on the plane z equals 0.
Why is that -1?
Outward pointing. So we have to face away from the surface, which means it has to point downwards. Let's see if we'll try to move these cameras. Get it all in one slide. now for that lateral portion. Again, we're dealing only with the surface. In this case, we're going to have a constant radius. It's only dealing with the surface of the lateral portion of the cylinder. But z is changing. Right? Z is going to go from 0 to 3. Normal vector. Just be 2 cosine theta, 2 sine theta, and 0. That was the whole part. Where are you getting it was 4x negative 2y squared z squared. Closed surface integral. Is the sum of all surfaces. So total net outward flux would be the sum of your net outward flux through each of the 3 surfaces. And vacuum surface integral, it's a double integral over your domain of the surface, with the parameterization. Evaluate your vector field at the surface. And so for the top, it was r cosine theta, r sine theta, and 3. Then it's dotted with your normal vector. dA. That up to give myself some more space. And over. Now for the bottom, actually, of course I don't have it on theorem. The evaluation is the same except z is now 0. Then double integral for the lateral surface. Because I have enough room. Evaluate it along the surface, which was what? 2 cosine, 2 sine, and z. Solid width. 2 cosine. I'm not going to have enough room. It's these 3 double integrals we have to evaluate. Luckily, most of them are easy. Do that first dot product. What is it?
9R.
It's just 9R, right? What about that second dot product? That's nice. Now for the third one. This is the pain. Because it's negative 2y squared, and y for the lateral surface is 2 sine theta.
16 cosine squared minus 16 sine cubed.
That's just zero, that middle one. That's really nice. Oh, by the way, that first one's also really nice. Do it this way. Because we can just write that like this, where dA is the polar differential for area.
What was the R then?
RdA is polar area differential. Right? R dy dx is your polar differential. Because you always get that extra R out of it. So that's what happened to it. That's just then 9 times the area of the region, which is a circular region. So even that doesn't require any evaluation. Radius is 2. 9 times 4 pi. It's that second one, or that third one, is going to be a bit of a headache. There's no z, so we can just evaluate in respect to z and get 3. Factor out that 16 as well. And this is where we're at. Take care of that cosine squared. Reduction identity. A half the quantity of 1 plus the cosine of 2 theta. Sine cubed, write it as sine times sine squared. Replace sine squared with 1 minus cosine squared. Let's write it this way. That should be a plus attached. There should be a 48 as well. So that's that. You move up there now. distribute that minus sign through. What's the period of cosine of 2 theta?
2 pi.
It's pi. Right, it's 2 theta, not just theta. Well, we're integrating from 0 to 2 pi, right? That length is not a multiple of pi. That's 0. What's the period of sine?
2 pi.
That's 0. Sine times cosine squared, you would do a u sub, where u is cosine. What's the period of cosine?
2 pi.
That's wrong. Oh, that worked out very nicely. You're just left with 1/2 d theta from 0 to pi. Isn't that just pi? (36 and 48). You have 84 pi. There is the left-hand side of divergence theorem. Now we need the triple integral, which means we need to go back, look at the solid that's being enclosed by our surface. We need to describe that solid. What coordinate system do you want to use?
Polar.
Polish for 2D.
Cylinder.
Cylindrical. This one's obvious. That's a cylinder. So cylindrical. Z. 0 to 3, right? Theta. 0 to 2 pi. R. 0 to 2. We also need divergence. What is the divergence? Divergence.
4 pi.
May I find divergence? I'm not there yet. We need the divergence of that vector field first before we can set up the triple integral. So I need to go back and look at the definition of divergence, which was when we did vector fields. Partial with respect to x the first term, plus partial with respect to y the second, plus partial with respect to z of the third. That's divergence. That was a couple weeks ago. I think it's when we did vector fields when we started this topic. That's the triple integral we're evaluating. And we described it in cylindrical. We need to write our integrand in polar. Not polar, sorry, in cylindrical. Your volume differential, R, dz, dr, d theta. Distribute that R through. This is a cylindrical box. Which means we really can just write this in any order we want. That term integrates out to 0. 4r plus 2rz dzdr. You know what? I'm going to factor that r back out. No, that should have been a 4r squared there, though, right? Because now I'm going to integrate with respect to r. That 4 minus 2z is a constant in terms of r. R squared over 2. Factor out the 2 as well. R squared from 0 to 2 is just 4, isn't it? That should be 8 pi. And that's what we're left with. 8 pi times 2 times 3 minus 9/2. Make life easy, let's factor out a 1/2. It's not right. Why am I writing minus 2z? That should have been plus 2z. I don't know why I wrote minus. That looks better. 12 and 9 is 21. 21 times 4. 84 pi. Our triple integral gave us 84 pi. Isn't that what the surface was? The surface integral? Divergence theorem has now been verified. For verification, so let's just do a smiley. So your choice on if you want to do a flux integral or the triple integral. However, just like with Green's and Stokes' theorem, where it had to be a closed path, divergence theorem only works on a closed surface. So something like what we just did would be closed. Notice the terminology. The region is bounded. If this was instead the region cut from x squared plus y squared equals 4 by z equals 0 and z equals 3, that is now an open surface. Which means divergence theorem would not have been applicable there. On quiz 4, the first question, just about everyone tried to use divergence theorem. First off, we hadn't even covered divergence theorem. Second off, there was an open surface, not a closed surface. So be careful. Outward flux of that vector field, y minus x, z minus y, and y minus x, across the cube, bounded by the planes x equals plus minus 1, y equals plus minus 1, z equals plus minus 1. First thing to ask yourself, is this a closed surface? Yes, it is. Right, all 6 sides of the cube are present. It is closed. You would also want to make sure that it is a piecewise smooth, which in our class it's going to be. Divergence theorem applies. What we want to do is first describe the solid that is enclosed by our surface. Well, it's the surface of a cube, right? So our solid is that cube. Negative 1 to 1 cross negative 1 to 1 cross negative 1 to 1. That is our cube. The next thing we need is the divergence of the field. What's that divergence? What is it? It's not just -1. I agree that's the partial of the first term. What about the second term with respect to y? It's also -1, isn't it? What about the third term with respect to z? So what's the divergence on the whole up? It's -2. And again, point out, for divergence theorem, not only does it have to be a closed surface, has to be oriented outwards, has to have outward pointing normal vectors. Again, you can make a slight change to this if it's inward pointing. We have outward pointing, so that's nice. We can't use divergence. So our outward flux would be that triple integral. But if you just integrate over W, the volume differential, isn't it just the volume of the solid? What's the volume of our cube? It's the length of one of the solids. 2 cubed. There's our outward flux. That's good. How many times can you yell, keep it in? There we go. There is the surface. Let's come over so we can take a better look at it. Rotate it. That's fine. We look from above. Across the cylinder. This. Oh, look at this again. I don't think this is closed.
Yeah, it's not.
I would argue this is not closed.
Both that chip is in.
Plane. Right here. Does that graboid close it? I don't think it does. You actually have to check the reference. I don't think that's closed. But I can still use divergence theorem a little bit. So here's what I'm going to do. I'm going to treat it as not closed and double check my resource, my reference, to see if it indeed is supposed to be closed, but I don't think it is. But we can somewhat use divergence theorem. And so what we can do is first treat it like it is closed. We're going to be using cylindrical coordinates. What is the solid it is enclosing? R is going to go 0 to 2, right? Yeah, we go 0 to 2. What's the distance from the origin? Okay. We're going to mess this one up. Yeah. Sorry, it would be 0 to 2. Because I'm only working with the projection. Yeah, the projection. Okay, I'm back. And theta goes 0 to 2 pi. And now for z. Z goes 0 up to r squared. Again, I'm treating it as if it was closed. If I just look at the top of the cylinder, assuming it's closed, it would go up to what? Z equals 4. Their intersection, right? Z equals x squared plus y squared. X squared plus y squared is 4 where they intersect, so z would be 4. Have normal vector 0, 0, r. So here's what we do. I'm just going to use F, I'm not going to write out the vector field. Treat it as if it was closed. So you find the flux through the closed surface. But subtract the surface, the flux that's coming through that top surface because it's open. What's our divergence?
Zero.
It's just x. No, it's not just x. X minus 1. Set this up. Here we go, what? 0 to 2 pi. We said r went 0 to 2, z went 0 to r squared plus r cosine theta minus 1 r z dr theta minus, oh, this one's going to be a pain. Zero, 2 pi, 0, 2. All right, well, I'm dotting it, so it's going to be 4r, right? Or negative 4r, rather. Z gets replaced with 4, and you take the dot product, the first two components are 0 anyway. That would be the setup. I'll let you evaluate that because I'm out of time. And I'll double check my source, but I'm fairly convinced now that I'm looking at this for like the 50th time, I don't know why I didn't see it before, that this is open. Right, but that's how you would get around that situation. Treat it as if it's closed, right? So even if we come back to here, let's say that was an open box, but it was only the top part missing. Just calculate the total flux of it being closed using divergence theorem, and then subtract the flux through the top, because that's where it was open. That's how you use divergence theorem around it, right? Rather than doing the 5 surface integrals, it's easier to do it that way. But I'm fairly certain that's open, that's what you have to do. So there's 2 questions left that we will finish up on Thursday, and I highly doubt it'll take me the entire time on Thursday to finish it up, which means there would be a little bit of time to ask questions. Before we leave, let's do this. last exam is Thursday, May 8th, 10:15 to 12:15 in this room. The exam is broken into 3 parts. The first part is mandatory. 50 points only covers topics since the second exam. That's the mandatory portion. Then you have 2 additional parts which will be optional. The second part is 2 questions from the topics of exam 1 with a chance to earn 5 points on the first exam. Second part, 2 questions from topics on exam 2 with the chance to earn 5 points on the second exam. Each question is worth 2.5 points, and it's all or nothing for those bonus parts. So you do have a chance to add up to 10 percentage points onto the first 2 exam scores. But it is completely optional, you don't have to do it. So technically the exam is not comprehensive, but it does have an extra credit comprehensive component. So use that when you're filling out your reference sheet. Decide if you want to do it or not. The exam will be 2 hours. Should be doable.
Sorry, so for the bonus parts, do we, for the first exam, the bonus parts, do we have to answer both questions to get the points, or like?
Each one's 2.5.
Okay.
So if you only answer one correctly, you get 2.5 points out of onto exam 1.
Okay.
If you get both correct, it's 5.
Got it.
I'll see you Thursday.